geometrical methods, and as you've worked out, the lead derivative is a way to look at the evolution of just about any quantity in a very nice compact form. Very powerful. And then we'll have a break, and then we'll hear something about, I think, biofilms. So, go ahead, Joe.
Yeah, I think I'll follow your introduction and talk a little bit about the big picture. So the idea is, suppose you had a smectic A, smectic C, mixture of these things, and you wanted to think about how your mixture is going to go, how it's going to dissipate energy and go to a critical point. Okay, it's going to be relaxing, and so you start thinking, okay, well, I'm going to need viscosity, I'm going to need some kind of elastic constants, I'm going to need about, I'm going to need a tensor viscosity, right? Because they have all these, it's all anisotropic, not isotropic. Okay, well then how are you going to decide to do that? You just throw in coefficients? How do you know when you put them in that your equation makes sense under even changes of orientation, under rotation? Okay, so this is a big question actually in turbulence. It goes back many years and people talk about objectivity of turbulence models. But here, objectivity, this property of having the entire equation transform properly, it was all being picked up from the Lie derivative and the use of the Lie derivative to formulate the Gaup equation using diamond. So we went grad, div, Lie derivative, diamond, and we made an equation. Okay? The thing about it is it's systematic. Suppose, for example, you had little disks that were interacting. Oh, that sounds like it might be something. Maybe little disks interacting with little rods. Or maybe little squares interacting with other little squares. Or even little triangles or little stars or something like that. How are you going to set up your gradient flow equation on those things? Okay, this will do it. Okay, this will do it, and it's just, you only needed to know, first of all, you already knew about grad and div. And anyone who's ever done a variational principle knows about Lie derivative, because variations are defined d by dt, d by ds at s equals 0 of something that you let introduced in s. So that's the variation, and the trick was to put the Lie derivative into the variation, because that's what variations are, and that way keep track of the transformation properties of the quantity you had. And there was only one more thing to do, which was to integrate by parts with the Lie derivative and define this diamond object and study its properties a little bit, but enough. Just from its definition, now it was enough to write down this equation so that you can put whatever you want to in for kappa. You can put little squares, little diamonds, little pyramids, and what this will do is take care of the thing that viscosity won't take care of. For example, when you have collisions of these things, do they transfer momentum? Yes, that's what viscosity does for you. Do they transfer angular momentum? Oh yeah, they do. But viscosity doesn't do that. Okay, well this will take care of that transfer of angular momentum as well. It'll also give you a way of incorporating the shapes of those things that are interacting. Okay, so that's the big picture. It's why we're doing this. It's the generalization of grad and div and delta to get to an equation which makes sense no matter what it is. For example, Randy, in his lecture, wrote down a tensor, which is a texture for Texture for what? For liquid crystals. Right, Randy? Okay. So, I'm ready big. So, the texture that Randy wrote was 1/2 epsilon ijk, or maybe it was ABC, right? You used ABC. Anyway, ABC is nice. Okay, times the 8th component of the director times the tensor components, this dB, wedge, dnc, which Randy wrote in vector form as epsilon ABC grad NA first, NA times grad NB cross grad NC. Oh, and there was something else to write here, right? Which is the area element, right? Because this cross product gives you a direction, and you won't get back to just a number until you put in the bases. This one here is expanding out the one above in some particular set of coordinates. This one here tells you everything you needed to know, right? It's do you remember how a determinant is defined? This is the determinant. Okay, it's exactly the determinant that Randy wrote. Now, how does this thing evolve? Suppose I set up some of this stuff, and it's going to undergo some kind of, this can be an exercise. So suppose I set up some domain that has this texture tensor in it, and it's going to relax to some critical point, because we're going to have to give it an energy, right? So we'll give it an energy that depends on the texture, and we can put anything else we want in here, because we can just keep adding these GOP equations. Okay, but so texture, ... density, pressure, and how are we ever going to get the equation for it? Oh, actually, we have it. Here's, just put in T for K, and this will be the equation. So that's what I mean by systematic. You know how something transforms. In this case, we know how Randy's texture tensor transforms. And there's no more worrying about what kind of tensor mobility or tensor viscosity or what you should have. It's just here. Okay, you need a mobility, you need an energy, and you need to know how the thing transforms. And then you can write down the equation for its gradient flow. And by gradient, we mean gradient divergence of diamond. Diamond takes into account all of the transformations that are encoded in the Lie derivative. Okay, so that's the GOP equation. So the question came up at lunch, how is this stuff connected with the generic model, the Ettinger model of non-equilibrium, they call it, thermodynamics, right? So it's Miroslav Gomela, Ettinger, there's another, then what? I think I forgot what his name is. Anyway, it turns out that what the idea for their non-equilibrium thermodynamics is a bracket structure, which is different from the Poisson structure, which is antisymmetric. Their bracket structure is symmetric. So how can we get from there to generic? Okay, so here's one way of doing it. suppose you have some functional f of kappa, and you ask for its time derivative. Okay, well, you know that that's equal to partial kappa partial t times delta f delta kappa, right? And we know from the Gauss equation that this is equal to minus the pairing of the Lie derivative with respect to mu of kappa diamond dE dk and d kappa, which we have prescribed. It has to be a vector field, so we put in this little thing that makes sure the indices are up, and then we write in kappa and df d kappa. Okay, so we're started now. So df dt. Oh yeah, we can use the properties of diamond now. There's this Lie derivative thing. We can put it over on the other side. And we'll get minus mu of kappa diamond d e d kappa delta e delta kappa paired with kappa diamond df d kappa sharp. Sharp because they have to be in dual spaces. And sharp takes this guy here, which indices down, into this guy, which has indices up. And this is this double bracket object, E with F, which when mu is linear in kappa, is the generic theory for a material with one tensor type of degree of freedom. In this bracket, as long as this guy is symmetric, so in particular, for example, if it's linear in kappa, let's make sure that this guy stays symmetric by assuming some class of mu's. Okay, so this is symmetric. This is the symmetric bracket. Okay, which underlies generic. Okay, so that's the answer to that question. And it's sort of interesting. This is this bracket has properties. So it's a Leibniz bracket. It's symmetric. It has to also be Leibniz to be part of generic. So Leibniz means that the double bracket of E times F with G is equal to E times F with G plus E with G F, right? And because of the properties of the diamond that this comes out, and the reason you can see it right away because the only place where E and F appear are under gradients. So of course, just go straight through. It satisfies the product rule, which is Leibniz. Oh, yeah. The other feature about this is that this guy is less than or equal to 0 for F equals E. So this energy is going to decay. Right? And it's going to go, when it decays, to a critical point of E, which is how we define gradient flows in the thermodynamic aspect. Okay, the other thing about this is nice, is it has a connection to Riemannian geometry. This is infinite dimensional Riemannian geometry. But if we take our double bracket, E with F, and just say, oh yeah, that's actually what I meant by a metric gamma sub kappa of delta E delta kappas with delta F delta kappa. And now you don't need any sharps, right? Because you use just the vectors coming from the variational derivative, since gamma, this is defining gamma in terms of something that transforms correctly. And we might as well write it down for completeness. It's minus mu of kappa diamond dE d kappa paired with kappa diamond dF d kappa. And the important feature is this minus sign, because it's what makes the energy decay. So this is a metric. It's a norm when E equals F, and it's negative definite. Okay, so when we write the equation, the Gauss equation now can be written as d kappa dt paired with something in the dual space to kappa is equal to gamma dE d kappa times the sharp of psi. And this will just give us our this just gives us back the Gauss equation immediately. Okay. All right. So a little bit more about this metric, right? It's negative definite. It gives energy decay, and it's symmetric. So it's a symmetric negative functional on the dual space of the kappas. Right? Because when you take variational derivative with respect to kappa, you go from the kappa space to the dual space. Okay, so let's evaluate this for a scalar function. Suppose kappa is a scalar function. So it's not a density now, it's just a function. Right? So if it's just a function, we don't have to carry d3x around with it. So then this Leibniz bracket is E with F is equal to minus integral dE d little f. Oh, so let's let kappa equal little f. D f d little f times the gradient of little f. No, it's not right. The gradient. Oh, there's that's right. Little f dotted with the gradient of mu of f. d3x. Okay, so if you look back at the equation for rho, you'll see that in the equation for rho, this is rho, this is mu of rho, the gradients were over here, dotted here. So the difference between a scalar and the Gauss equation for a scalar and a density is, in this case, these guys are densities. These guys can take a gradient. You have to have a scalar to take a gradient. Okay? These guys are functions. They can take a gradient, whereas and then you integrate this guy. These guys are densities. Okay, so let me write the equation. So the Gauss equation in this case is d by dt of f is minus the Lie derivative with respect to mu of f diamond, the EDF, just writing down the same thing as usual, sharp acting on F. Okay, and when we work this guy out, it's equal to minus dE d F grad mu of F sharp dot grad F. Oh, look at that. See, the Lie derivative of a function with respect to a vector field is a vector field dotted into the gradient. That's the equation. Okay, and so this says this is a characteristic equation. This is the speed. Okay, so it says that F is a constant along dx dt equals this velocity, the EDF grad mu of F sharp. Very simple. Something with this velocity here is just displacing F as a function of time, so we can just write it down as, well, the Lie derivative for scalar functions is just a vector field dot with gradient, and you're in. Okay, and this object here, right, this is our signal speed. Okay. I have just enough space to also write the solution. F of x and t, if df, the EDF and mu of f are smooth, so that this vector field is smooth, then it has solutions which are sums over delta functions. Okay. So, and the average of F, which is K star, right? K star F, the convolution, filtered version of x and t, will be this thing with K of x and QA. Right? Because when we convolute with the Green's function on delta function, it just evaluates the Green's function. Okay, so how do the solutions look? Suppose we start with a bunch of these delta functions on a real line with a bunch of different weights. Okay? Can you imagine what it's going to look like? Well, it's going to depend on your choice of this kappa, or sorry, K, the kernel. Okay, but so let's just have a kernel that falls off exponentially at a rate alpha. Okay, so that the kappas are little shapes that look kind of like a TP maybe. Then here's how it works. Okay, so we have a bunch of initially have a bunch of delta functions. We smooth them with K, so we have a bunch of shapes like the kernel. And see, these guys are moving off more or less at the same speed because they're at the same height. Same height means same weight. Speed's proportional to the weight. These guys are moving into each other immediately. So this is a waterfall plot as usual. You know, each one is plotted at a time step above the other one. So these guys are interacting in a non-trivial way, even though each one is moving along a characteristic if you have it by itself. So, okay. So that's what everyone's trying to do, except it's feeling all the other weights through this Green's function. Okay, so let's just look at 2. Okay, we just start one with weight +1 and one with weight -1, and simulate the equations that fall from this delta function assumption. Then they collide and they stick. They just clump. Okay, well, they're clumping. Yeah, what?
Quick question, actually. What you do here is basically you get F as smooth end, and then you have that characteristic speed that.
Yeah, so you put this F into
Right.
this equation, you
Right.
pair it with the smooth function, and you'll have some delta functions and some derivatives of delta functions, and set the coefficients equal to 0 separately. Oh,
But, you know, if you get your characteristics actually smooth instead of actually F, then you never actually collapse you never allow these guys to collapse. You essentially get closer and closer. The characteristics that just keep condensing to each other, concentrated, but they never cross. Then
Yeah.
then you could have existence, uniqueness.
I think the problem is they don't emerge either. If you start with the smooth initial condition, these guys have the delta functions emerge, and they do this kind of interaction. If you don't have that, then the delta functions are actually not in the class of solutions. Okay, and it so happens that this Goff equation does what it was ordered to do. I was interested in emergent singularities, and this produces emergent singularities. If you switch around, then those singularities are not in the solution anymore.
Which one we consider more physical?
What?
Which one we consider more physical?
Oh, neither one is really physical. It's what we're studying is, in kind of a different world. You know, what happens in a world where delta functions can emerge from smooth initial conditions? Because we're interested in what happens when blow-up occurs. Everyone is always saying, well, let's stop when blow-up occurs. And I'm saying, no, let's keep going. Blow-up gives us an opportunity to study the interaction of the singular solutions.
But if you do that, you never get blow up, right? If you average that characteristic.
Well, the characteristic is already smooth, right? Because we've already assumed that that this vector field is smooth. And we got that by choosing dEdF to be a function, like depending on f bar, and mu to be a function depending on f bar. So this guy here is a smooth velocity, and it acts on a gradient of f. And if you look at this, here's f, here's smooth, here's f. So if you put in delta functions, you can have a delta function on each side. Okay, and then that solution is admitted. If that's not true, you can't put in a delta function because you have to be multiplying delta functions. I think I should move along. Okay, so let's see, I'm going to go back to this picture here. I guess I want that. Okay, so, except I'm going to call psi rho now, I think. Yeah. Okay, so you see what was happening here is there's some asymmetry. This was psi, this is the magnetization. these are the equations that are satisfied. And these are the equations for when you have two kappas. Okay, one is a density, and the other one is a magnetization. Oh, we didn't even think about that, did we? We were just thinking about shapes. Okay, but what if they want to do that, right? What if they want to anti-align? Or, I mean, you can also choose an equation of state so they want to align. And then, so now they're colliding and they're exchanging some kind of magnetic force interaction. Okay, so we have these equations. So let's write our singular solution. So we write the mass density as rho of x and t equals weight sub rho of t delta function of vector x minus q of t. And let's for a second, let's drop all the a's. We'll sum over the a's later, okay? Because it's easier to write the equations if we say, okay, so our parameters here are the weight, w sub rho, and the position, q of t, would be all the weights in all the positions. And we have a magnetization density, which is a, you know what it is, one form vector, one form density. Magnetization density m of x and t is equal to a vector weight sub m of t times the delta function of the same position. Okay, so these are particles that are moving along at the same position, and they're carrying mass and a weight of magnetization. Okay, so if we substitute them into the equations, into the GOP equation, we get omega rho sub dot is 0, omega m dot is omega m crossed with mu m crossed with the EDM, all evaluated at x equals q. Okay, and in fact, so this guy rho is picking up the divergence piece like we had before, and for the magnetization density, it's picking up the cross product part. So the magnetization pieces are interacting like this. And there's one thing left, which is what about q dot? Q dot is this v of q and t. So it says this v here, each particle at a given q is moving with the velocity, which is the transport velocity in these equations. Okay, and then one simulates the equations. Okay, so when you do that, you can start out. See, here's the density one that we looked at before. It's a different one, but it's for this problem, and it has quite a bit of going the wrong way. Quite a bit of these features here, and these features. Okay, so this is the way we kind of expect the density peaks to go. And but we start with the magnetization vectors at t equals 0 that point in random directions. Okay, so how do magnetization vectors clump? Okay, well, they start organizing themselves and eventually just point in one magnetization direction, according to these equations. Okay, and these are those equations. I think I have another point I can make. Yeah. I have time for this. I was describing here particles, aggregation of particles with magnetic properties. So I now want to put my particles along a curve. So I wanted to see the interaction of curves of magnetic particles with each other. So I'm going to have strands of magnetic particles now. Okay, and so the trick is to find out how you strand these things along when they're delta functions. Right? So you want to inject into here another variable which will be along the strand. Okay, so let's call that variable S for strand, and we'll put some little magnetization at each point with some weights. Those are the parameters. And we'll look at how this distance from some initial frame r changes with time and the strand variable. Okay, so to do this, it's as easy as pi. Rho of x and t along the strand and in 3 dimensions is the integral of the weight rho times s and t. Weight rho of a function of s and t. See, here we only had it be a function of t. But now we're going to spread it out along the strand and integrate over s. So we'll put in also a delta function of x minus q of s and t ds. Okay, so let me call this q. Okay, so that's how this guy is changing. And the magnetization, the function of x and t, will be, well, we'll string it out again. It's like this one here, but we put in s and t and integrate. So it's the weight, the magnetic weight, is the vector, depends on s and t. It's the delta function of x minus q of s and t ds. So all we did was to string these along was to take the particles and give them a dependence along a curve and call this s equals 0 and this s equals 1, and now your curve has been defined. Okay. I'm not going to write down the equations for them. They're very similar to these equations, except everything, instead of having a t, has an s and a t. Okay, because you have to know the motion of every point along the strand. Okay, so how does this look? Okay, if we simulate these equations, so let's simulate the situation where we have two strands interacting with each other. and each of them has a little frame that can rotate. And once, if we put it, actually I didn't do it, it didn't put it in a magnetic field. That would be interesting. But let them interact through a potential. Okay, so they want to attract each other. Okay, and as they attract each other, the magnetic interactions will be stronger. And it looks like this. So if you start out with these kind of organized and these random, for these two curves at t equals 0, so we're running up to t equals 50, and you can see the curves attract each other, and when you get close enough, then they align their magnetization. As time goes on, they will come closer, and the magnetization will be more aligned. This cannot be done with viscosity. Right? You've got to have control of the geometry. It's not just the usual kind of gradient flow. Okay. I have time to talk about, I have 2 or 3 minutes to talk about oriented particles. So let me talk about that to finish. So now let's not magnetization, but let's let the particle have a shape and let the shapes interact with each other. Okay, so let's let E of kappa be equal to the sum of E sub rho plus E sub sigma, another variable. Okay, where E sub rho is 1/2 the integral rho at x prime times some kernel g x and x prime dx prime. Okay, so now we got a bunch of particles with different locations, and this is their density at those locations. And now let's put in the shape interaction. E sigma is equal to 1/2 the integral rho of x prime k of x and x prime, and then let's put in some feature which allows the particles to have M-fold symmetry. Okay, so let's put in this sigma as an orientation variable, and let's write this as, or an angle, and let's write this as m times sigma of x minus sigma of x prime. I'm a cosine of that. So now each time it goes around, right, you have, if you have 5-fold symmetry, then you see this thing going around 5 times as it turns around once. Okay, so you put that on, and simulate that, and you see what happens if you start out with, this is rho and this is sigma, you start out with a Gaussian distribution in rho, things clump in kind of a peculiar form. They're not clumping in a circular way. They're clumping in this kind of patterned way. And we start out here with sigmas, the orientations, being just random, and they also clump in kind of a structured way. Okay, so this is with m equals 5. Okay, so m equals 5 is like a 5-sided star. You know, and have you ever been in like a button shop or a tinsel shop where you have trays of these little plastic objects, circles, triangles? Okay, if you try stars, and they float on water, these things. So each one floating on water depresses the water, right? And they look downhill to each other, and they start moving toward each other, clumping. That's that K for this thing. And actually the K it's a Bessel function for circles. And here's how it looks. you start with some stars arranged in some kind of regular form. This is floating on water, and these are pictures of an experiment where we just floated. We arranged the stars, lowered a net into the water. They start floating, and after 10 minutes, they start clumping. Like that one clumped to that one. I guess maybe it's one of the nearest ones. These three clump together, and see where's the brown one? The brown one's still there. Where's the other brown one? I don't see it right now. These two clump together, and these four clump together. 30 minutes, okay, after another 20 minutes, these clumps are growing, okay, and after an hour, you see this pattern. So what happens is that they can look downhill to each other. When they come closer, they're depressing it more and more. And if they land at the point to point, then they'll slide one way or another to keep getting closer. Okay? And so there will be this tendency to make branched trees. Okay? This cannot be done with viscosity. Okay. Thank you very much.
You take a question or two?
My job is done.
So if you have circles, you say they
Yeah, if you have circles, they clump together with a few gaps in the middle because it depends on the rate at which they come together. If you have squares, then the squares can come in corner to corner, but then they'll slide, okay, to minimize the periphery, minimize the area actually, right, because of not the area, the periphery. And the squares are a little bit less jagged. They go off and they can form long rafts, or in rafts which come out straight away from them, okay, because they have this fourfold symmetry. The fivefold symmetry is the one that intrigued us.
That enters the cave.
What?
That enters the cave.
Yeah.
And become a,
Yeah, it's this one here. M equals 5.
okay.
Question there?
Yeah, could you do something like this experiment against an overall background flow to see what happened then? So I guess you could treat that theoretically, certainly.
This was done extremely carefully to let the water sit for days and be covered, right, with glass plate and so forth, because we didn't want to have any flow. On the other hand, we could do the simulation with no trouble. And the simulation, this is taking such a long time. You'd have to have a very slow flow, or else you just see it swirling all the stars together and they don't have any time to interact. But yeah, so that they will demix if you put in a flow.
I think T is waiting outside, and we need to be back by 3 or 5 past 3. Okay, so thanks, Daryl.